Okay, so let's start. Hey, everyone. So in this talk, we'll talk about solid principle and clean architecture, how to apply these principles. So let's start with the short presentation. Here you can find my contacts. I work at the New York Times. I'm a remote engineer there. I work here from Italy. I'm a Google developer expert for Android and Kotlin. Here you can find my contacts. Today, we'll see the solid principles and how to apply them in the clean architecture. We'll see the solid principle with a concrete example. Fortunately, every time we have to show an example in a tutorial or in a talk, it's quite difficult because usually, for example, this tweet says that in a tutorial, how to draw a horse is something like draw two circles, then draw the legs, then the face, then the hair, and that's all. You just need to add some small details. So to avoid doing something similar, we'll see a concrete application, let's say, an Android application. This talk is not about UI at all. So this is the application. It just shows the current location, the current weather, and the forecast for the next week with the minimum and maximum temperature. In case we don't have internet connection or the location is not available, we show an error message. In case we are in the middle of nowhere, so we have the location, but there aren't any cities next to the location, we show something like no city found, and then we have the temperature and the forecast for that place, even if there aren't any cities. Okay, so this is the main code that we'll see. It's a use case. It defines a suspending methods, get city data. This method returns the string that will show in the UI. It's a suspending method, so we are using the coroutines. In the body of the method, basically we are retrieving the last location. Then we are retrieving the cities in that location using async, so it's a background task, let's say. Then the temperature in the same location. Then we await for the result of the cities, and we combine the cities, the first city, or an error message if no cities are available, and the temperature with the string. We don't have any return because it's Kotlin. So this class uses two collaborators, two objects, collaborators. The location manager to retrieve the current location and the cities in that location, and the temperature repository to retrieve the temperature. The two collaborators are injected inside the class as constructor parameters. So here we are using the dependency injection, because we are not creating the collaborators inside our class, but they are external constructor arguments. So this is basically the dependency injection without any frameworks. Why are we using the dependency injection? It's because we want to test this class. This class, whether use case, contains the main business logic of the application, and we want to test it. So we have a test like this. Here I'm using mock. This is a typical test where we create a mock of the collaborators. Then we use the dependency injection to create the object that we want to test, passing the two collaborators, the mocks of the two collaborators. And then inside our method, we just define how the collaborators works, which values they should returns. Then we invoke the method that we want to test, and we verify the result. So this is basically is always called arrange, act, assert. So we define the collaborators, we act, so we invoke the method that we want to test, and then there is an assertion to verify that the result is what we are expecting. Okay, so let's go back to our example. This is the main business logic of the application. And as we saw before, we are using two other classes, two other interfaces. So we have an interface for the location manager and another interface for the temperature repository. And obviously, we need two concrete implementations. Okay. So the Android location manager is the implementation of the location manager that basically uses a context to use the fused location client and the geocoder. And then basically the two methods are the mapping of the standard Android calls to the coroutines word. So we are using suspend coroutines and with context. And these are two suspending methods. Okay, then we have got the implementation of the temperature repository. This is the code. Again, we are just using Kotlin and the coroutines. And we are basically executing two server calls in parallel. So the first one to retrieve the forecast and the second one to retrieve the current weather. And then we just map the values and calculate the minimum and the maximum temperature. And we return a temperature object. Again, dependency injection. So this repository doesn't create the API object directly, but it's a constructor argument. Again, so the open weather temperature repository is using a weather API. That is just an interface defined using some retrofit annotations. Just one thing to note, here I'm using the retrofit snapshot. So I define the method as suspending or returning just the real object instead of the ferred. This is not available yet, I think, in the official retrofit release, but it's just in the snapshot release. Okay, let's go. So this is just the big picture. We have got so the use case that uses two interfaces, two collaborators, and then there are the implementations. The use case is used by a view model. So we have just our view model that creates all the dependencies and just invokes, using a view model scope, the method to retrieve the string to show in the UI. Then it uses a live data to show the string in the UI. The live data obviously is used by the activity, but it's on the top left, but we'll not see the activity, we don't need it for this. It's not the point of this example. So, okay, we have 8 classes. How do we organize these classes into modules in our Android project? We can create an app module that contains the activity and the view model. Then there is a domain module inside the Android Studio project that contains just the weather use case. So it's the domain because it contains the business logic of our application. Then there is a location module that contains the interface and the implementation of the location. A weather module that contains the interface and implementation of our repository. And there is an API module that contains all the retrofit stuff to execute the server calls. Okay, we know that in Android Studio we can define a module like an Android module, an Android library, or a standard Java or Kotlin library. Here, obviously, the app is an Android application. The location is an Android library because we are using the context and the geocoder and other Android stuff. And the domain must be defined as an Android library because it depends on the location. So when we have a dependency on an Android library, we need to define the module as an Android library. So the domain is an Android library too. Even if, probably, basically, the domain doesn't contain any Android specific stuff. But we just need to define it as an Android library because we are using the location module. Okay, what's the main difference between standard Java Kotlin modules and Android modules? Basically, usually the Java Kotlin modules are more testable and reusable. This doesn't mean that the Android modules are not testable or not reusable, but if you have a 100% Java Kotlin module, you are sure that you will be able to test it on a Java virtual machine without using an emulator, so it's faster and it's more testable. And then it's more reusable because you can use it in both the Android module or the standard Java Kotlin modules. Okay, so let's start to talk about the solid principles. This is a paper written by Robert C. Martin, also known as Uncle Bob, in 2000. So it's quite old right now. This paper defines the solid principles. Solid is an acronym, and there are 5 principles. In this paper, there are the 5 principles, even if the acronym is not there, because the acronym was invented, let's say, by Michael Feathers some years later. So the S on the acronym SOLID stands for single responsibility. This is quite a classical principle, let's say. It says that a class should have one and only one reason to change. This is similar, let's say, to cohesion and decoupling, that are basically 2 main principles of the object-oriented programming. So a class should have one and only one reason to change. Let's see our example again. So here, basically, there are many classes, and each class has a single responsibility. Maybe the only one that has 2 responsibilities is the location manager and the Android location manager. But probably for this example is quite a good organization, I hope. Then there is the O that stands for open-closed. These principles say that you should be able to extend the class's behavior, to extend the class's behavior without modifying it. This is even older than the solid principle because it was in a 1988 book, Object-Oriented Software Construction, written by Bertram Meyer. So it's quite old, and basically it says that we should use the inheritance in a good way, let's say. So an example is that we have got an implementation, an interface with 2 implementations. If we want to change something, we don't modify the implementations, so the code is closed for modification, but is open for extension. So we add another implementation of the same interface, maybe with the factory to hide the implementations. Next principle is the list of substitution. It says that derived classes must be substitutable for their base classes. Usually we don't talk about the list of principle, but we talk about the violation of this principle. So let's see the most famous, the most common example of the list of a list of substitution violation, and is this one. We have got a rectangle class with 2 sides, with a date, 2 fields, and an area method. And then we know that a square is a rectangle, so we want to create a subclass of rectangle and call it square. But the square manages just a single side. So we don't have in the constructor 2 arguments, but we have just 1 side's argument. And we can modify it because there are 2 var fields. So we want to be sure that even if we change something, it's still a square. So in the setter of the width and the height, we check if the value is changed, and we modify the other side to be sure that it remains a square. looking at the code, it seems that there is something weird. So why is this hierarchy a list of substitution violation? It's because if we have got a rectangle and we calculate the area, and then we modify the height, we double it, we expected that the final area is the initial area multiplied by 2, because we have just two rectangles, one next to the other. But then we can reuse the same rectangle variable, and we can assign a square to this variable, because the square is a rectangle, so this code compile. And then we can calculate again the initial area. Then if we do the same thing, so we double the height, we expect that the final area is the initial area multiplied by 2. In the reality, it's not true, because when we change one side of the rectangle, inside the implementation changes the other side as well. So the final area is the initial area multiplied by 4. So we can't use a square instead of a rectangle, even if a square is a rectangle. So this is the list of substitution violation. Basically, this principle says that we have to use the inheritance in a good way without creating a mess, basically. Then there is the interface segregation. That says that we should make fine grind interfaces that are client specific. So basically, we shouldn't create a big interface with a lot of methods. It's better to create a lot of small interface with just a few methods in each interface. And again, our interfaces are quite small, so we are using this principle. And the final one, that is the most interesting in this talk, is the dependency inversion. At the beginning of the talk, we talked about dependency injection. That is, the name is quite similar. And usually when we talk about dependency inversion, we talk also about inversion of control. There are two connected principles. But in this talk, the D in the solid principles stands for dependency inversion. That is a bit different. So let's see this principle. Dependency inversion basically says, if you search somewhere, you can find that the basic definition of this principle is this one. Depend on abstractions, not on concretions. So we should depend on the abstractions, so interfaces, and not on concrete objects. So based on this definition, we can take a look at our example again, and we see that the main dependencies are against the interface. So it seems that we are using the dependency inversion. But if we search again this principle, we can find another definition that says that high-level modules should not depend upon low-level modules. So it's quite different, and here we are using an important keyword, important word, that is modules. So basically here we are talking not about classes dependencies, but about modules dependencies. So let's take a look to our example again. And let's see these dependencies between domain and location. So we have the use case that depends on the location manager, and then the Android location manager that implements the location manager. Here the high-level module is the domain, because it's the business logic of our application, and the low-level module is the location, because here the location knows how to retrieve the location and how to retrieve the cities in a location. And so the high-level module depends on the low-level modules. So we are not using the dependency inversion. How can we change this example to use the dependency inversion? The name inversion should suggest that we should invert these dependencies, and we can do it just moving the location manager interface to the domain module. In this way, we haven't changed anything in the code. We have still two classes and one interface, but we have inverted the dependency between the two modules. So the location module that is the low-level module, now depends on the high-level module that is the one with the business case, the business rules, let's say, our use case. So let's go back to our example, and let's talk about modules. So this is the actual structure. So the location depends on the domain. The entities on the bottom is just a module that contains some Kotlin data classes. We can invert weather and domain relation in a similar way, moving an interface. And we can invert the weather and API. So the API will depend on the weather. And then we can move the entities here, because it's used by domain and everyone else uses the domain. So on the left, there is the initial architecture. On the right, there is the final one, the final result. We say that on the left, we have 3 Android modules, app, domain, location. On the right, we can have just 2 Android modules, because the domain, we don't need to define the domain as an Android module anymore, because it doesn't depend anymore on the location. So it can be defined just like a Java or Kotlin module. Basically, the code is the same, but we are just inverting some dependencies. So basically, in the domain, in both examples, the domain doesn't contain any usage of the Android classes. But on the left, we are not using Android classes on the domain as a code convention, because we know that we don't want to use them to test it in a Java virtual machine test. On the right, on the example on the right, we are not using Android classes in the domain, and if we try to use it, it doesn't compile. We get a compilation error because it's not an Android module. So this is an important differentiation. Okay, let's add some colors. So the example on the left, usually, this is the diagram of the architecture. It's a layered architecture. The dependencies are from top to bottom. The example, the architecture on the right, is the clean architecture. So it's a circle, and basically there are 2 important rules. These are on the original clean architecture blog post written by Robert C. Martin, and it was written in 2012, so 7 years ago. The first important rule is that source code dependencies can only point inwards. So the stuff on the external circles depends on the stuff on the internal circle. So the domain just depends on the entities. The UI depends on everything, more or less. And the other rules is this. There is no rules that says that you must always have just 4 circles, let's say. So the clean architecture is not strict. You can have any number of levels. So if you need more levels, you can add it. And it's not strict that it doesn't tell you where to add certain class. There is just the dependency rule that the dependencies can only point inwards. That's the important stuff. Okay, looking at the example, there is something to talk about, that is module by feature or module by layer. In this example, it seems that the clean architecture suggests us to create a module for each feature, for each layer, sorry. So all the UI stuff in the same module, or the data source in the same module, all the domain in the same module. In a real example, probably the final result is something like this. So we have multiple feature module, multiple domain module, and multiple, for example, one API repository that uses 2 APIs that can be defined in multiple modules. So usually it's defined like a module by featured layer or something similar. But again, there is not a rule. You can decide how to implement the modules. So the pros of this architecture, the most obvious pro is the framework independence, because as we can see from the diagram, the framework, so the UI, for example, is in an external module. So if we want to use another UI framework, not in our case probably, we can just change the external layer. Or, for example, the data source is on the bottom. So if we are using, I don't know, a room, we want to use something else, we don't need to change the domain, the business logic that is in the internal circle. We can just replace a module that is in the external circle. So the business logic of the application, that is the important stuff in the application, is independent from the framework that we are using. And this is really important, and especially if we want to use Kotlin multi-platform, for example, because in this way we are sure that the circle in the center can be reused in multiple platforms using Kotlin multi-platform, because they can be defined as a pure Kotlin module. We don't have any dependencies on the UI, on Android, or an external stuff. The second pro is the one that I was talking about, so architecture versus code conventions. So in both examples, in the domain, we weren't used any Android code to test it on JVM, but thanks to the clean architecture, it's the architecture that forces us to avoid using that. In the previous example, it was just the code conventions. So writing on the wall or on the somewhere in the office that say that you shouldn't use Android code in the business layer. And the final pro is about this book that doesn't exist yet. So excuses for not writing unit test. I think that on Android, the typical excuse is that I don't write unit tests because they are slow. So I can't wait a lot of time every time to run a JUnit test because I want to run the unit test a lot, many times. So using the clean architecture, again, the important stuff, the business logic of the application is in the center, in the domain layer or in the entities. So in these modules, there are no external dependencies. There are any dependencies on the Android stuff, so we can test it on JVM. And basically, when we run a test in the domain, we just need to compile just the domain, the entities, and there is just a few classes in the class path. So we can use test-driven development to write the code in the domain layer. And this is the most important pro of the clean architecture, in my opinion. That is not just an architecture to organize the code in a better way, but it's an architecture to enable test-driven development, even in big projects. Usually, the con is that we need more code, because sometimes we need some extra interfaces, sometimes we need some mapping from one class to another. Here, for example, we can't use the Android location in our business logic, so we are forced to create a new location class, data class that is in our entities, because we can't use the other one. So we need probably some extra classes, but it's not usually a big problem. So these are the pros and the cons. Can we achieve something similar in other ways? Yeah, probably. So this is the clean architecture. So the location is an Android module. The domain is not an Android module. We can do something similar, for example, creating 3 modules. So creating another module just for the interfaces. This is probably not the clean architecture, but it's quite similar. And we have something similar, the same pros. Probably the only con in this architecture is that in the interface module, we can't use the classes defined in the domain, but basically is similar. We can leverage the API implementation feature in Gradle. So we can define the a low-level module, the dependencies on the low-level modules can be defined using the Gradle implementation keyword. So basically, if you are using the retrofit, for example, in the implementation in the low-level module, we can define retrofit as implementation, so we can't use a retrofit in the domain module. So it can be useful, but unfortunately, in this way, we still need to define the domain as an Android module, because the Android dependencies can be defined using implementation because it's a different module. Okay, so these are the pros and the cons. You can find the example of this talk on my GitHub account. There are 3 branches. The first one is classic, I think. It's the original example. Then there is the clean branch with the clean architecture example. And there is a third branch with the Dagger implementation. To use Dagger in architecture like the one that I described here. Probably I'll write a post about it soon. Then there are the first paper by Robert C. Martin, another article, interesting article of 2005, and the original blog post about the clean architecture, written by Robert C. Martin. And then 2 years ago, I think, something similar, Robert C. Martin wrote a book about the clean architecture. Usually the book is the starting on something. If you think about the TD, test-driven development book written in the 99 something, it was the beginning of the test-driven development. Here, in the reality, this book was published after the clean architecture was already used, but it's quite good. And that's all. Thanks for your attention.